Firstly, the introduction. The COVID-19 pandemic caused by SARS-CoV-2 spread rapidly worldwide, prompting extensive research, rapid vaccine development, and ongoing public health measures to manage and mitigate its impact. With this dataset, it's providing critical insights into patient characteristics and outcomes. Next is problem statement. Identifying individuals that have COVID-19 remains challenging, so our project aims to develop a model to accurately predict whether the patients have COVID-19 or not, based on symptoms, medical history, and demographics. We have two objectives, which is the first one is to determine the best classification model that predicts COVID-19 based on their present symptoms, medical status, and medical history. The second objective is to determine the key factors affecting the mortality of COVID-19 patients. Next is data acquisition and data understanding. The dataset is downloaded from Kaggle, and the data were collected from various sources including patient information, hospital records, and publicly available dataset regarding COVID-19 cases, recoveries, deaths, and other related metrics. Dataset is also used in various research studies analyzing the spread, impact, and trends of COVID-19 across different regions and demographics. This dataset was written by me, NAZIR. The dataset consists of 4,375 instances and contains 31 attributes. The data has numeric type and nominal type, which consists of 20 numeric and 1 nominal data type. The data does not have missing values.
Data preparation is crucial for making sense of data in machine learning. It's about cleaning up raw data so that it's tidy and ready for analysis. First, open Weka. Click on Open File and we open our dataset, which is COVID-19 dataset. Our dataset contains 4,375 instances. We only use 80%, which is 3,500 instances for pre-processing and preparing the data. There are 20 numeric attributes like sex, pneumonia, and others, which are measurement or counts, and 1 nominal attribute, date died, which is indicate categories like dates or labels. We have to study both of the numeric attribute and nominal attribute. For each numeric attribute, we look at statistics like the smallest minimum value, the largest maximum value, the average, mean, and how much the value vary from the average, standard deviation. Next, we have to look for missing value. Click on the filter panel. Go to Unsupervised Attribute and replace missing value. Click on Apply to check for any missing value. Upon loading the dataset in Weka Explorer and applying the Replace Missing Value filter, we found out that there are no missing value in this dataset. Next, the important part is identifying noisy data. First, we use Detect Outlier using interquartile range. Click on Filter, select Unsupervised Attribute, interquartile range, and click on Apply. Why is it important to remove noisy data? Noisy data refer to random errors or meaningless value that can affect our analysis result. Here, we can see in our COVID-19 dataset, there are no outliers were detected by the unsupervised filter. However, we can see here, there are 1,758 instances as extreme value. We have to consider for removal to enhance the accuracy of our data analysis. To remove the extreme value, we have to click on Filter, click on Remove with Value, and then change the attribute indices to last and click on Apply. We have to remove the outlier and extreme value to have more accurate dataset. We also delete date died variable from COVID-19 dataset because it is irrelevant for our analysis. After completing data cleaning in Weka, save the clean dataset as COVID-19 dataset clean. Here, a preview of our first 20 rows of the clean dataset to show the improvement made. Then, we move to transformation, which is first, we have to perform normalization, which is we use min-max normalization. Click on Pre-Process tab. In the filter panel, select Unsupervised, Attribute, Normalize, ensuring the range is set to 0, 1. Click on OK and then Apply. After normalization, the data is transformed to range uniformly between 0 and 1. Next, we have to perform discretization. Click on Pre-Process tab. In the filter panel, select Unsupervised, Attribute, Discretize. we have to change the bins to specific attribute. For example, age. We want to change for 3 bins, which is young, adult, and senior. Click on the Save button to save the discretized dataset as COVID-19 dataset and change the file type to CSV. We have to further processing in Excel. Open the Save CSV file in Excel. Use the Find and Replace feature to convert numeric value in attribute like age to categorical labels such as young, adult, and senior. Save the changes in Excel. Load the update CSV file in Weka. For the other attribute, we have to use numeric to nominal. Filter unsupervised attribute numeric to nominal. This is because from the original dataset, we already have 2 categorical such as obesity attribute. The data already describe 0 as no obesity and 1 as have obesity. The table below presents a comparison between classification and clustering technique. For our group project, we have chosen to use classification. Classification is the process of developing model from our data to categorize or predict the outcome. We will discuss the result obtained from 2 main approaches. Firstly, cross-validation. This involves splitting the data into k folds, which we will employ k equal to 10 and k equal to 20 folds. Next, another approach is to use percentage split to split the data into training and testing set based on percentage. We will evaluate our model using both 70:30 split, where 70% of the data is used for training and 30% for testing, and another one, 80:20 split, where 80% is for training and 20% is for testing.
After we have prepared the training dataset, we start our model development process. First, we need to load the data into the Weka Explorer. Next, we click the Classify tab and click Choose. And then go to the trees, select J48 since we wanted to use J48 algorithm. In our group project question, we are required to do the cross-validation with different folds k equal to 10 and k equal to 20. First, we will perform k equal to 10, which is 10 folds. Then we click the Start button. On the right panel, Weka will give us the analysis of the data. We also can get the accuracy right here, which is 78.473%. Now we know that cross-validation with k equal to 10 produces the accuracy of 78.473%. For cross-validation of 20, we just repeat the earlier steps and change the fold to 20. But now that we know that cross-validation of k equal to 20 produce 77.9564%. For percentage split, we do the same thing. We still use J48 algorithm, but we use the different selection of the test option, which is the percentage split. Firstly, we do the 70% percentage split. Click Start and it shows the accuracy of 76.4818%. For 80% percentage split, we get the accuracy of 76.4368%. Next, we use naive Bayes algorithm. Choose button in the classifier box and select Bayes and navigate to naive Bayes. In the test option, set cross-validation with fold k equal to 10 and k equal to 20. It shows the accuracy of 75.8898% for k equal to 10 and 76.062% accuracy of k equals to 20. For the percentage split, the accuracy of 70% percentage split is 76.4818% and 76.4368% of 80% percentage split. Next, we use a random forest algorithm. Choose button in the classifier box and select trees and navigate to random forest. In the test option, set cross-validation with fold k equal to 10 and k equal to 20. It shows the accuracy of 77.9564% for k equal to 10 and 78.3582% of accuracy k equal to 20. For the percentage split, the accuracy of 70% is 74.3786% and 77.2989% of 80% percentage split. Next, we generate 3 visualizer for J48 as the best model. First, right-click here and select Visualize tree. The tree will pop up and you will get the result. Based on the table, the best model is J48 model as it has the highest accuracy in both the cross-validation for fold k equal to 10 and k equal to 20 and percentage split 70% and 80%. J48 consistently shows highest accuracy across different evaluation methods, indicating consistent performance. J48 may be considered the best model due to its interpretability, simplicity, and balanced performance. A confusion matrix is used to evaluate the performance of classification model. This is the data for J48 confusion matrix. From the confusion matrix for J48 model, the cross-validation for k equal to 10, the TP is 100, TN is 1267, FP is 87, and FN is 288. For percentage split 70%, the TP is 29, TN is 371, FP is 17, and FN is 106. This is the data for the naive-based confusion matrix. And also, this is the data for the random forest confusion matrix.
In the data reduction process, attributes were chosen based on their correlation with the outcome variable and information gain. Attributes with coefficients above 0.02, such as age, diabetes, and intubate, were considered significant, while those with low or negative correlations, such as sex and USMR, were excluded. This approach ensured that only the most relevant attributes were retained, optimizing the predictive model. The Ranker plus InfoGain attribute eval model prioritized attributes based on information gain, selecting important ones like age and diabetes. InfoGain attribute eval was chosen for its ability to measure attribute importance accurately, enhancing the model's predictive power. The greedy stepwise and CFS subset eval model use greedy stepwise to evaluate attribute subsets efficiently, selecting age and diabetes. Paired with CFS subset eval, it ensured the chosen attributes were both individually predictive and collectively non-redundant, improving model efficiency. The best first plus CFS subset eval model used best first to comprehensive attribute subset exploration, confirming age and diabetes as key predictors. Combined with CFS subset eval, this method optimized attribute selection by maximizing predictive power and minimizing redundancy. Excluded attributes, such as USMR and sex, did not meet the significance threshold and were removed. The simplification of the dataset allowed for more focused analysis and improved model performance. Dataset is reduced by removing attributes that were not selected. This is the before and after of the reduced data. There are different accuracies for each model. For the J48 decision tree model, the accuracy for cross-validation with fold k equals to 10 is 79.22%, and for fold k equals to 20, it is 70.93%. For the percentage split method, the accuracy is 75.72% for a 70% split and 77.87% for an 80% split. For the naive-based model, the accuracy for both cross-validation with fold k equals to 10 and fold k equals to 20 is 76.46%. The percentage split method shows an accuracy of 76.10% for a 70% split and 76.72% for an 80% split. Lastly, the random forest model has an accuracy of 78.53% for cross-validation with fold k equals to 10 and 78.30% for fold k equals to 20. The percentage split method gives an accuracy of 74.76% for a 70% split and 76.44% for an 80% split. Based on this accuracy matrix, the J48 decision tree model is the best among the three due to several factors. It achieves the highest accuracy of 79.22% with k-fold cross validation k equals to 10, demonstrating superior performance. J48 also shows consistent accuracy across various testing methods, indicating robust performance. Additionally, it is inherently interpretable, providing clear decision rules, making it easier to understand and apply. Although random forest shows competitive accuracy, J48's combination of high accuracy, consistency, and interpretability makes it the most suitable choice. The J48 Decision Tree for predicting COVID-19 based on cross-validation for K equals to 10 considers diabetes, age, and ICU status. Decision tree for all reduced data set is the same. This is the data that we acquired for confusion matrix for J48 model. Next, this is the data for confusion matrix for NIF-based model. Lastly, this is the data for random forest confusion matrix.
Specification analysis is about reviewing various models on full and reduced datasets, shows performance differences by model and data handling. The J48 decision tree model performs best with 79.22% accuracy on the reduced dataset using 10-fold cross-validation, slightly better than 78.47% on the full dataset. The naive-based classifier also improves with the reduced dataset, showing 76.46% accuracy with cross-validation compared to 75.89% on the full dataset. The random forest model is robust, achieving 77.96% accuracy on the full dataset and 78.53% on the reduced dataset with cross-validation. This study highlights that reduced datasets generally enhance performance, particularly with cross-validation, by potentially eliminating noise or irrelevant features, underscoring the importance of dataset and reduction and cross-validation in improving model accuracy and reliability. Next, moving on to the prediction of the new data, the J48 model demonstrated exceptional performance by accurately predicting all instances in the provided test set as COVID-19, perfectly aligning with the actual outcomes from the original data for the 20 instances shown. This consistency indicates a high level of accuracy for these specific cases, showcasing the model's capability in correctly identifying COVID-19 instances. For all instances from 1 to 20, the predicted outcome is 2.1. Given the context, this likely corresponds to a specific classification in the model. If 1 represents no COVID-19 and 2 represents COVID-19, then 2.1 indicates a prediction of COVID-19 for all instances. Therefore, the predicted outcome for each instance is COVID-19, as shown in the table above. So, as the conclusion, this project identifies the J48 decision tree model as the best for predicting COVID-19 outcomes based on patient symptoms, medical status, and history due to its high accuracy, precision, recall, F-measure interpretability, and robustness in handling complex medical data. Key mortality factors include age, comorbidities like diabetes and cardiovascular disease symptom severity, respiratory distress, and gender, with males having higher mortality rates. The dataset from NAZIR on Kaggle includes 4,375 instances and 21 attributes, providing comprehensive patient data without missing values. The project addresses the challenge of accurately identifying high-risk individuals by developing classification models to predict COVID-19 risk and identify mortality factors, involving rigorous data preprocessing, model development, and evaluation. The insights from these models aim to improve risk stratification, timely intervention, and resource allocation, highlighting the importance of robust healthcare systems and global cooperation in managing pandemics, and reinforcing the need for ongoing public health and medical research efforts.